Hello everyone, I am Honar Gupta, a PhD scholar at IIT Kanpur. Today we will discuss about the content of fourth week of fundamentals of supersonic and hypersonic flow. From this week I slightly changed the pattern. So in the last weeks I used to generally talk about what was taught in the class, but in this week I will discuss based on the problems. And the problems which I will discuss is related to the last year's problems of this course, Fundamentals of Supersonic and Hypersonic Flow. First question is, the relation between Nusselt number and Stanton number is given by option A, Ch equal to Nu Re upon Pr, option B, Nu equal to Ch Re upon Pr, option C, Nu equal to Ch Re Pr, and option D, Ch equal to under root Nu upon Re Pr. So what will be the relation? It was taught in the class. The relation will be C, Nu equal to Ch Re Pr. We will see how. Nusselt number Nu is given by Qwx upon Ke Taw minus Tw. And Stanton number Ch is given by Qw upon Rho e Ue Haw minus Hw. Here subscript W is for wall, Aw is for adiabatic wall, E is for age of boundary layer. And Qw is the heat transfer. Local heat transfer rate, which is nothing but heat transfer energy per second per unit area of wall, which is given by K rho T by rho Y at wall. And K is E is the thermal conductivity at the edge of the boundary layer. Haw and Hw are enthalpy at the adiabatic wall and wall, and Taw and Tw are temperature. So we will start with Nusselt number definition. Nu equal to Qwx upon Ke Taw minus Tw. So what we will do, we will multiply and divide by Rho e Ue into Cp. I was discussing this one problem, the relation between Nusselt number and Stanton number, which is given by Nu equal to Ch Re into Pr. So I was deriving this only. So Nusselt number is given by Qwx upon Ke Taw minus Tw. So I will divide numerator and denominator by Rho e Ue into Cp. It will become so here I have multiply here, and so here also Rho e Ue and Cp. And this x term I have taken it here, and this K is taken here, and I have also multiplied and divided by mu. So this term, if you see, Rho e Ue x upon mu, this is a definition of Reynolds number at location x. And if you see this, Cp mu e upon Ke, this is nothing but Prandtl number. So it becomes QW upon rho E UE. Cp into TAW will be enthalpy. This is for calorically perfect gas. For calorically perfect gas, enthalpy is given by Cp into T. Similarly, Cp into TW will be HW. So we got this relation QW upon rho E UE HW minus HW into RE into PR. And this is nothing but Stanton number. So Nusselt number will be equal to CH RE into PR, which is option C. We'll see other problem. In a non-similar compressible boundary layer, the local skin friction coefficient on the wall depends on where epsilon equal to integration 0 to x rho e u e dx. Option R, A equal to G dash epsilon xi comma 0, G double dash xi comma 0, F dash xi comma 0, F double dash xi comma 0. So what will be the answer? Anybody knows? Local skin friction coefficient is CF. So it will depend on what? Which of these? F dash is nothing but U upon U and G is H upon He. So in which of these terms it will depend? It will depend on F double dash xi comma 0. We'll see how. So local skin friction coefficient is given by Cf equal to tau W upon half rho E UE square, where tau W is given by mu dou U by dou Y at wall. This tau W is nothing but shear stress at wall, and it is given by this equation. So now first we will see for laminar steady compressible boundary layer what is Lee-Dorot densities transformation. Only using that transformation we convert xy coordinate to xi comma eta. So xi is given by integration 0 to x rho e ue mu dx, and eta is given by eta equal to ue upon under 2 xi integration 0 to y rho dy. If you see this xi equation, it is only function of x. This is function of x only. And if you see this eta, it is function of both x and y. This is function of y, and this xi is function of x, so it is function of both x and y. And in non-similar compressive boundary layer equations, we have used u equal to ue f dash xi comma eta. We are using this because we have to find dou u by dou y at the wall. So we have to use the definition of u and integrate it or differentiate it with respect to y. Now if we see from the definition of differentials, then dou y equal to dou y dou xi into dou xi by dou y plus dou y dou eta into dou eta by dou y. We have seen before that this xi is only a function of x only, and this eta is function of x and y both. This is function of x only, so dou xi by dou y equal to 0. And if we differentiate it, okay, we don't need it, so and so this term will be 0, so we will get dou eta by dou y dou eta, and dou eta by dou y will be, this term is constant, and if we differentiate it we will get rho, so we will get ue rho upon under root 2 xi dou y dou eta. Now we can find dou u by dou y, or say tau w, wall shear stress. It is given by mu dou u by dou y at wall. So at wall this mu will become mu w, and dou u by dou y we can write it using this equation. So it will become u e upon under root 2 xi, and at wall this rho will become rho w dou u by dou eta at wall. So it will become mu w ue rho w upon under 2 xi, and this term if you see here, dou u by dou eta will be dou u by dou eta f dash plus ue f double dash, and at the wall if you know the boundary condition for this boundary layer equation, you might know that f dash xi comma 0, this 0 is eta equal to 0 at wall, it will be 0, so this term will be 0, so we will get only ue f double dash, ue dou f dash upon dou eta at wall, this is f double dash. This ue and this ue will be ue square mu w rho w upon under root 2 xi f double dash xi eta at wall eta equal to 0. You can see from here also, this eta is given by ue upon under 2 xi integration 0 to y rho dy. So at wall y will be 0, so eta will be ue upon under 2 xi integration 0 to 0 rho dy. This term will be 0, so eta will be 0 at y equal to 0. So at wall eta equal to 0, then tau w will be ue square rho w mu w upon under 2 xi f double dash xi 0. And from the definition of CF, local friction coefficient, CF equal to tau w upon half rho e ue square. And if you divide it by half rho e ue square, this 2 will go up to rho w mu w, ue square will cancel upon rho e under 2 xi f double dash xi 0. We will get this equation. So from this you can see that it depends on this f double dash xi 0. F double dash xi 0. Does anyone has any doubt in this one?
No, sir.
Okay. Then we'll see the next question. Compressible boundary layer equation for flat plate involve ODEs, the highest order derivative in which are first order, second order, third order, fourth order. What is the answer for this one? Compressible boundary layer equation for flat plate. Okay, then we will see what are the equations first. So compressible boundary layer equation for flat plate is given by C F double dash whole dash plus F double dash equal to 0 and C upon PR G dash whole dash plus F G dash plus C UV square upon HG F double dash whole square equal to 0. Here dash is for derivative with respect to eta, not partial. And C is given by rho mu upon rho e mu. This constant is called Chapman reversal factor. And here F dash not only function of eta. F dash eta equal to u upon uv and g eta equal to h upon he. So if you see the equation, if you see the first equation, which is momentum equation, C F double dash whole dash plus F double dash equal to 0. Which order equation is this one? First order, second order, third order, fourth order. Which?
Second order.
No. See again. You are seeing the second order here or here. Based on that, are you telling? But see again, there is one more derivative here also.
Yes, sir.
So it will be, if we take the derivative, it will be C dash F double dash plus C F triple dash plus F double dash equal to 0. So you can see that this is the third order equation. This equation is third order. And this equation, if you see, you can directly see here this is the second order and term. And if you also take the derivative of this term also, you will get second order term only. So this will be second order equation. So in the question, what was asked? The highest order derivative. What will be the highest order derivative? It will be the third order. So,
Third order.
So its answer will be third order. Any doubt in this question?
No, sir.
The next question is laminar boundary layer thickness varies approximately as m equal to Mach number at the edge of boundary layer based on me square, me cube or me to the power 1 by 2. What will the answer for this? It was taught in the class.
ME square, sir.
Now, its answer will be m square. There is one more question. I will explain both questions together. Boundary layer thickness at the given value of ME. TAW is adiabatic wall temperature. Is approximately the same for insulated flat wall. TW equal to T adiabatic and cold wall. TW is less than T adiabatic. Is more for a cold wall. TW is less than T adiabatic than an insulated wall. TW equal to T adiabatic. Is less for the cold wall. TW is less than T adiabatic than an insulated wall. TW equal to T adiabatic. Is inversely proportional to the wall temperature. Which will be the correct answer for this one? In this one, the comparison is done for boundary layer thickness for cold wall. For this, wall temperature is less than adiabatic wall temperature, and for the insulated wall or adiabatic wall. So what will be the answer?
Sir, I think it is inversely proportional to wall temperature, sir.
No, it will not be this answer. Wait, wait, let me check for this one. How about temperature? No, it will not be this one. Any other answer?
Sir, it's less than cold wall, sir.
No, it is less for the cold wall. We'll see how. First, we'll see this one, how it varies approximately. So these are boundary layer profile for adiabatic wall and isothermal wall. So if you see this adiabatic wall, this y-axis is y upon x under root rex, and x-axis is u upon ue. And here this number mentioned are Mach number. So you can see that as Mach number is increasing, here this u upon u equal to 1 is, you can say, is for boundary layer thickness. So this number is given boundary layer thickness only. Or you can say this, it is given del upon x under root rex. So you can see that as Mach number is increasing, it is increasing very rapidly. The boundary layer thickness is increasing very rapidly. Similarly, for the isothermal wall also, if you see that the boundary layer thickness is increasing very rapidly as we are increasing the Mach number. So our boundary layer thickness is directly proportional to m square. And if you see the both figure, let's say this is m infinity equal to 20, let's say for 16. This case, for cold wall means TW is less than T adiabatic. For this case, this number is between 20 to 30. Its boundary thickness is between 20 to 30. And for the adiabatic wall, if we see, it is greater than 60. So for the adiabatic wall, it is higher. For isothermal wall, it will be lower. And the reason for this is that I will show one profile. These are the temperature profile for the same Mach number. Adiabatic wall have the higher temperature. Here you can see it is temperature is greater than 40, and here the maximum temperature is between 10 and 12. So for the adiabatic wall case, temperature for adiabatic wall case is greater than temperature for isothermal wall inside the boundary layer. So if temperature is high, temperature is low in this case, so density inside the boundary layer will be high. Density for isothermal case will be greater for density for adiabatic case. So if density is high, it means to accommodate the mass flow inside the boundary layer, it needs the less thickness. For the same mass flow inside the boundary layer, it needs less thickness, because mass flow will depend on density. So if density is high, it means for the density and volume. So if density is high, it means for the same mass flow rate, it needs less volume. So it will accommodate the mass flow in the thinner boundary layer. So boundary layer thickness will decrease in this case for the cold wall. And as we increase the Mach number, the temperature also increases. As we, if for the same Mach number, if we cool down the wall more for two cases, if we cool down the wall more for some case, then boundary layer also will become more thinner. This is the reason. Is there any question in this question problem?
No, sir.
Okay. Then the next question is the peak temperature within the boundary layer for a cold wall case. Increases rapidly with increase in Mach number ME, decrease rapidly with increase in ME, varies inversely with ME, or varies with under root ME. What will the answer for this?
So increase rapidly. So
Now, it will increase rapidly with increasing ME. So these are the temperature profile for adiabatic case and isothermal wall. Uh, this question is for cold wall case, means isothermal wall, and TW upon T is equal to 0.25, means cold wall. So if you see this figure, the maximum temperature is increasing with Mach number. So this maximum temperature is increasing with Mach number. And you can see also that it is increasing very rapidly. This is 8 to 12 and 8 to 16, 12 to 16. It is increasing rapidly, then increasing Mach number. And this is the answer for this question. But we will also compare the case with the adiabatic wall. So in adiabatic wall case, the temperature at the wall is higher than a isothermal wall, and this temperature is also increasing with Mach number. In case of isothermal wall, what happens is that at the edge, the temperature will be equal to H. At the edge of boundary layer, temperature will be equal to the edge temperature, and due to the viscous dissipation, this temperature will increase inside the boundary layer and it will reach a one maximum value. And due to the isothermal wall condition, this temperature will again become equal to the wall temperature. And in the case of adiabatic wall, the edge temperature at the edge of boundary layer, this temperature will be equal to TE, and at the wall, this temperature will become maximum. And this temperature is also called equilibrium temperature also. And the more we increase the Mach number, the more will be the viscous dissipation inside the boundary layer, and the more will be the maximum temperature, peak temperature. Viscous dissipation happens because at the wall, the temperature has to reach, velocity, let's say for supersonic flow, velocity is very high, where at the wall it has to reach the slip condition. That means E equal to 0 and B equal to 0. So the large amount of kinetic energy is lost, due to which this viscous dissipation happens. Is there any doubt in this one?
no, sir.
Let's see the next question. Reynolds analogy links the following: RE and M, Reynolds number, Mach number, local skin coefficient and Reynolds number, Nusselt number and Stanton number, with local skin friction coefficient and Stanton number. It is very simple question. It links the local skin friction coefficient and Stanton number, and you can say it is defined by the ratio of these two, CH upon CF. And for the compressive flow, CF is a function of Mach number, Prandtl number, gamma, wall temperature ratio, and Reynolds number. And CH is also a function of Mach number, Prandtl number, gamma, wall temperature, and edge temperature ratio, and Reynolds number. And if you take the ratio of this, it will become function of Mach number, Prandtl number, gamma, and TW by TE. This is the Reynolds analogy. For the incompressible flow, it will become 1 by 2 Prandtl number to the power minus 2 by 3. This is an important result. And we will see that in the slides that generally for the compressible flow also the CH and CF is not, there is not much difference from this value minus 2 by 1 by 2 PR to the power minus 2 by 3. For compressible flow also all difference is between 2%. So generally for quick calculation we also take this for compressible flow also. Wall shear stress tau W increases rapidly with increase in Mach number, decreases rapidly with increase in Mach number, varies as under root ME, varies as 1 upon under root M. What is the answer for this?
Sir, decreases rapidly with increase in Mach number, sir.
No, it does not decrease. So how did I reach at this conclusion? Did you reach based on the CF?
Yes, sir. As yes, increase.
CF decreases but it will increase with C. So this is the plot of CF under root REX versus Mach number, and it is taken at different TW by TE, and also for adiabatic plate also. So if you see that if we are changing this TW by TE also, there is not, first thing to notice that it is decreasing with Mach number. See, we have increased that Mach number from 0 to 20, and this value is, let's say for this case TW by T equal 0.5, it is decreasing from around 0.67 to approximately 0.45. So this is not too much decrease. And second thing is that one thing is that this for incompressible this value will be this CF under root REX will be equal to 0.664 for incompressible case. And as we are increasing the ratio of TW by TE, thus the CF is decreasing. This you can see let's say we have two walls, one with TW by TE as 0.25 and other is TW by TE as, let's say, 1. And if we see the boundary layer profile, velocity profile for both these, one thing is to note, it's that uh, the temperature. If wall is more cold, if wall is more cold, then temperature will be lower. If temperature will be lower inside the boundary layer, the density will be high. And if density is high, it means boundary layer will be thin. It means boundary layer will be thin. It means delta will be less for more cold wall. So for this is, let's say, UE here and here UE. So this is lambda for 0.25 TW by TE delta, and this is delta for 1. So delta 1 will be greater than delta 0.25. So as boundary thickness is here low, so dou U by dou Y at wall here will be greater for dou U by dou Y wall for this case 1. So this dou U by dou Y will be higher, it means CF will be higher. From the definition we know that CF is nothing but tau W upon half rho E UE square. So if this value is high, it means CF is also high. So for the same Mach number, CF will be high for colder wall. CF will increase as TW by TE decreases, and CF will decrease as Mach number increases. But this is for CF. Now we'll see for tau W. We have to see for wall shear stress. For wall shear stress, TW equal to half rho E UE square CF. Now we'll write it in terms of Mach number, half rho E. UE can be given by ME square gamma R TE. You know that definition from Mach number, M equal to UE upon under root gamma R TE. So using this we got this, and if you see that rho E R TE from the ideal gas equation, PV equal to rho E R TE. So we will get it gamma by 2 EE ME square CF. So here, if let's say Mach number is increasing, you know that CF is decreasing. But if you see that change in CF is very small, but Mach number is this for the tau W, we have term Mach number is square. So this term will increase rapidly than the decrease in this CF. So our tau W will also increase rapidly with increase in Mach number. Is there any doubt?
No, sir.
Okay, move to the next question. Here two statements are given. First one is both CF and CH decreases at Mach number M increases. And second one is both CF and CH increases as the wall is cooled. A statement 1 is true, statement 2 is false, statement 1 is false, statement 2 is true, statement 1 and 2 are both false, statement 1 and 2 are both true. What will be the answer for this? One thing to notice, I already explained about CF. What will happen to CF if ME increases and if wall is cooled? what will happen to Cf if Mach number increases? I told just before, if Mach number increases, what will happen to Cf? Cf will decrease. Cf is decreasing here as Mach number is increasing. So Cf will decrease as Mach number increases. And if wall temperature decreases, then what will happen to Cf? Cf will increase.
Sir,
Huh?
sir, your video is not continuous. It's stuck. It is stucking, sir.
It is stucking. Now it is okay, or is there any issue?
Sir, now okay, sir.
Now okay. Okay, so I will repeat this.
While you were taking lecture, it issue arises.
What?
Now the signal is okay, sir.
Okay,
When you're talking lecture, the issue arises, sir.
okay, okay. Now it is okay now?
Yeah, yes, sir.
Huh. So we have to tell what happened to both Cf and Ch when Mach number increases and wall is cooled. It means Tw by Te decreases. So for the case of Cf, we already saw that when Mach number increases, Cf decreases. So on this plot, when Mach number increases, Cf decreases. Cf is decreasing. And when wall temperature decreases, it means it is cooled. When wall temperature decreases, you can see that Cf is increasing. Cf is increasing when wall is cooled. So one thing is true that Cf decreases as Mach number increases, and Cf increases when wall is cooled. For Cf it is true. You have to see what happened with Ch. This is plot for Ch under Rex and Mach number. If you see it here, it has the almost same trends as Cf. If you see, Cf was also decreasing like this, and Ch is also decreasing like this. Only thing is that in Ch the decrease is less than Cf, and uh, if you see that when wall is cooled, it means that Tw by Te is decreasing, then you can see that Ch value is also increasing. And with the Mach number also, if you see that when Me is increasing, where Me is increasing, then you can see that Ch is decreasing. So for both of these, you can see that Me is increasing, then Cf and Ch both are decreasing. And when Tw by Te is decreasing, then Cf and Ch both are increasing. So you can see that this statement is true because both are decreasing as Mach number increases, and this is also true because both are increasing when wall is cooled. So both these statements are true. So option D will be the correct one. If you, let's say if you don't remember for Ch also, you might remember the Reynolds analogy which we saw before. It was Ch by Cf equal to half Prandtl number to the power minus 2 by 3. This is the analogy. this one, half pi to the power minus 2 by 3. So random number is, you can take a constant also. So this value is constant. So if you can see if CH is increasing, then CF will also increase, and if CH is decreasing, then CF will also decrease. So both shows the similar trends. This we can, I told also that we can use this for compressible also, because the change in only of about 2% from this value for the compressible flow. This is true for incompressible. Is there any doubt in this question?
No, sir.
Next question. For a cold wall, TW is less than T adiabatic. If QW is the heat transfer occurring at the wall, then QW is less than 0. QW depends on K, thermal conductivity, dou T by dou N, wall, temperature gradient at the wall, and the wall area. And QW equal to 0. QW is greater than 0. Which one will be the answer for this one?
So QW less than 0, sir.
Why will it will be?
Sir, in cold wall the heat transfer occurs, so it will less than 0, sir.
It is cold wall. This wall is cold, so this wall temperature will be less than surrounding temperature. So in which direction the heat transfer will occur? It will occur from wall to surrounding or surrounding to wall.
Surrounding to what?
It will occur from surrounding to wall, then heat transfer will be positive or negative.
Positive.
So it will be positive. So this D will be the answer. In this one there are multiple answers. So this is not possible. If this is true, then this is not true. This is not true. We have to check this B only. And QW, we already know that it is equal to Ka dou T by dou N as the wall. There is heat transfer rate. So this is also true. B on B. We can see from this figure also. This is for temperature profile for the cold wall, for TW by T equal to 0.25. So if you see that at the cold wall, the surrounding temperature will be higher, and inside the boundary layer there will be one point where there is the peak temperature. So if the temperature is high in the surrounding, the heat transfer will occur from surrounding to the wall, and as heat is transferred to the wall, it will be QW will be greater than 0. Is there any doubt?
No, sir.
Is there any other question you wanted to ask? Any doubt in the lectures also? Okay, no question. Then I discussed about some of the theories which was taught in the class. First we'll see lambda compressive boundary layer. This is given for study 2D, and there was no body force was considered. Continuity equation is given by dou u by dou x plus dou v by dou y equal to 0. X momentum is given by rho u dou u by dou x plus rho v dou u by dou y equal to minus dpv by dx plus dou y mu dou dou y. By momentum is given by dou p by dou y equal to 0. From this equation, you can see that if, let's say, on a surface there is one boundary layer, then at a location, pressure does not change normal to the that surface. So if whatever pressure is at the wall, it will be the same at the edge of the boundary layer or any point in the between. So this pressure does not change with respect to y. It means pressure is function of x only. That's why in this x momentum, this dou p by dou x is written as this dp by dx. And one more thing, whatever is pressure at the wall, it will be same at the edge and any other point of the boundary layer. So we have directly substituted this pressure to edge pressure at edge. So we are taking the pressure at the edge of the boundary layer in this equation. So whenever we are solving the equation, we don't need this equation because we have already taken the effect of this equation in this x momentum equation. X moment energy equation is given by rho u dou h by dou x plus rho v dou h by dou y equal to dou y k dou t by dou y plus u dp by dx plus mu dou u by dou y to the whole square. Here also similarly we have taken the ordinary derivative, not partial derivative. There are some boundary conditions which we need to solve it. If at the wall there is no slip, then the boundary condition for velocity will be u equal to 0, v equal to 0. And in case there is a mass transfer at the wall or some translational cooling, ablation, then this velocity perpendicular to the surface will not be 0. We will take v equal to vw, whatever is the velocity at the wall. For the temperature, there can be two types of boundary condition. One is the isothermal boundary condition where temperature at the wall is fixed, T equal to Tw, and another is adiabatic boundary condition where this gradient of the temperature at the wall is 0, dou T by dou N at wall equal to 0. And at the far field, y tends to infinity, velocity will become equal to edge velocity and temperature will become equal to edge temperature, edge of the boundary layer. This E here is edge of boundary layer. In the quest of finding the cylinder profile, we do the one transformation xy to the xi eta. First, I will tell what is the cylinder profile. Generally, what happens? This is boundary layer. Then at each location, the velocity profile will be different. So for the similar profile, what will happen that this is for x and y. For let's say some xi and eta coordinate, our boundary layer profiles becomes the same. This figure is not good, but model profile is same at each location, so it does not change with xi or eta. Velocity will change only with eta, but different xi it will remain same. So there is one transformation, lead or direction transformation. It will not give this similar profile, but it can be used for finding the similar profile for various different cases. For generalize this compressible boundary layer equation, it will not give the similar profile, but for different cases like flat plate, cylinder, it will give the similar profile. So here this chi will take it in three different 0 to x, ue, 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 dx, and eta equal to ue upon under 2i integration 0 to y rho dy. We saw this before also. Here you can see this xi is function of x only, and this eta is function of x and y, because this xi is function of x and this is the function of y. We can find this derivative of xi and eta with respect to x and y. Dou xi by dou x will be rho e, ue, and ue, and dou xi by dou y will be 0. Dou eta by dou y will be ue rho upon under root 2 xi. From the partial differential relation, dou y dou x can be given by dou y dou eta into dou eta by dou x plus dou y dou xi into rho xi by dou x. Dou eta by dou x, dou xi by dou x we found before, it was rho e, ue, and ue, dou y dou xi plus dou eta by dou x into dou y dou eta. Dou y dou y equal to dou y dou xi by dou y plus dou y dou eta into dou eta by dou y. We have seen that dou xi by dou y equal to 0, so it will become dou eta by dou y into dou y dou eta. And dou eta by dou y we found before is ue rho upon under root 2 xi, and it will come into dou y dou eta. Now we introduce some function like u by ue equal to f dash xi eta, and this f dash is nothing but derivative with respect to eta, partial derivative with respect to eta, which is dou f by dou eta xi eta. And one string function is given by using the continuity equation. It defines the conservation of mass. So dou phi by dou y equal to rho u equal to rho ue f dash. We put the value of u from here, and dou phi by dou x equal to minus rho v. Now if you find the dou phi by dou y, it will be equal to, from this relation, dou by dou y, we put this term, so dou psi by dou y equal to ue rho upon under 2 xi dou psi by dou eta, and this term is equal to nothing but this rho UE f dash. So this rho E and UE will cancel, and dou psi by dou eta equal to under 2 xi f dash. If we integrate it, then this is independent of eta, and this term is derivative of eta only. So we will get under 2 xi f plus one constant which is function of xi. At wall phi will be psi will be 0 because if at wall there will be streamline, and f will be 0 because v is equal to 0, and so we will get k equal to 0 also. So psi equal to under 2 xi f. For the energy equation, we will take one more function hy he equal to g xi eta, and there are some boundary condition for eta equal to 0. Eta equal to 0 means wall, means y equal to 0. If we see from here also, at y equal to 0, this limit will be from 0 to 0, so we will get 0 only, eta equal to 0. So at wall y equal to 0, so f xi 0 equal to 0 and f dash xi 0 equal to 0. It means u equal to 0. This is for u equal to 0, and this will get v equal to 0, and g xi 0 equal to gw. This is for isothermal wall condition, or we will get g dash wall at wall equal to 0. This is for adiabatic. So that means dou g by dou eta at wall equal to 0. And when eta tends to infinity, it means y tends to infinity, f dash equal to 1 and g equal to 1. F dash equal to 1 means e equal to u, and g equal to 1 means h equal to he. So we will substitute all these functions and these derivatives. We will get these boundary equation. These are the compressible boundary layer equation. Now, and this can be solved using these boundary conditions. For a flow. So we can simplify this further for the flat plate. For the flat plate, UE will be the constant, and the each velocity will be constant. So dou UE by not dou, this is d UE by d xi equal to 0. So this term will become 0, this term will become 0, this term will be 0, so our equation will become C f double dash dash plus f double dash equal to 2 xi f dash dou f dash by dou xi minus 2f by 2 xi f double dash. This is the momentum equation, and energy equation is C by PR G dash dash plus F G dash equal to 2 xi F dash dou G by dou xi plus F dash G by Hg dou Hg by dou xi if He will also be constant. So dHe by dou He by dou xi also will be 0. This term will also be removed. Minus T dash dou F by dou xi minus C V square upon He F double dash square. So we got these two equations, and in this equation if you see we have these terms which are function derivative with respect to xi, and if we want the similarity solution, this equation should be independent of xi. So if we take f as function, we take f as function of eta only and g also function of eta only, then these terms will not be in the equation. And we will get the equation as C F double dash dash plus F double dash equal to 0, C upon PR G dash whole dash plus F G dash plus C V square upon H F double dash square equal to 0. These are the compressive boundary layer equation. For flat plate. And if you see that we saw this before also, this is the third order equation, and this is the second order equation. So we need total boundary conditions 3 plus 2 equal to 5 in eta to solve these equations. So at the ball, what we know, at ball eta equal to 0, and the ball boundary condition will be f0 equal to 0 and f dash 0 equal to 0. This is corresponding to b equal to 0. This is corresponding to e equal to 0. One more condition will be for g. G0 value equal to GW wall for isothermal case, and it will be equal to not equal to this one, or we will get dgy d eta at wall equal to 0, or g dash wall equal to 0. This will be for adiabatic wall. These are the two and one of these three boundary conditions. And when eta tends to infinity, f dash eta will be equal to 1 and g eta will also be equal to 1. This is for g equal to v and this is g equal to g. These are the boundary conditions. Using this boundary condition, we can solve this equation. For solving this, we can use the footing method with, let's say, Ranjagupta method also. So, in footing method, we will take these three boundary conditions and we will assume for f double we will assume value for f double dash and g dash. So for footing method, initially we know the value of f0, f dash 0 and g0 or g dash 0. So let's say we know the value of g0. So we will assume the value of g dash 0 and f double dash 0. Assuming this, we will march in eta and found the value of f dash eta and g eta when eta tends to infinity. If it is equal to 1, then our assumed value is correct. If it is not equal to 1, then we will update these values and again use the marching method till we get the we satisfy this boundary condition of eta equal to eta tends to infinity. Is there any doubt till now?
No, sir.
Is there any other question related to the course? Okay, so when you solve these, you will get the solution similar to this only. I formed the velocity profile before. You will get the velocity profile same as this one. For the isothermal wall, and temperature profile same as this one. And rest of the properties like skin friction coefficient, stunting number also can be found. this chi. For the flat plate, this chi is given by integration 0 to x rho e u dx. For the flat plate, these are constant, so we'll simply get rho e u dx from 0 to x, which will be equal to rho e mu e into x. Is there any question, or I will stop till here? Okay, then I will stop here. Thank you. See you in the next class.
Thank you, sir.